In this video, we're going to talk about drawing constitutional isomers. So the first question is, what are constitutional isomers? Very simply, compounds that have the same molecular formula, but different structures, so the atoms are connected differently, are called constitutional isomers. Now, constitutional isomers, even though they have the same molecular formula, because they are connected differently, they are different compounds with different properties. One example is dimethyl ether and ethanol. So they both have the formula C2, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, one oxygen each, so they're both C2H6O, but because they're connected differently, they are different compounds, right? Just one example of a property that's different, the boiling point of dimethyl ether is negative 23 degrees Celsius, whereas the boiling point of ethanol is 78 degrees Celsius. Their other properties are going to be different as well. So one important thing to keep in mind when you're asked to draw constitutional isomers is valency. So the atoms that we're going to deal with most often in organic chemistry are carbon, nitrogen, oxygen, hydrogen, and halides, so fluorine, chlorine, bromine, and iodine. And these atoms, at least when they're neutral, tend to form a predictable number of bonds. And so carbon generally forms 4 bonds. We call it tetravalent. Nitrogen generally forms 3 bonds, so we call it trivalent. Oxygen is divalent, forming 2 bonds, and hydrogen and the halogens are monovalent, meaning they tend to form 1 bond. And so when you're drawing these constitutional isomers, it's really important to keep this in mind. You always want to give carbon 4 bonds, nitrogen 3 bonds, oxygen 2 bonds, and hydrogen and the halogens should only get 1 bond. Now, organic chemistry is largely the chemistry of carbon-containing compounds. The reason organic chemistry is so rich and there are so many different carbon-containing compounds is because carbon is fairly unique in that it can make long chains, so we can chain lots of carbon atoms together. Hydrogen, nitrogen, oxygen, halides, most other elements can't do this under normal conditions. So when you're drawing constitutional isomers, make chains with carbon atoms, not the other atoms. So for example, I could make a compound like this where I've got 4 carbon atoms chained together, but I wouldn't want to make a compound like this, where I'm stringing a whole bunch of oxygen atoms together, or nitrogen atoms, or certainly hydrogen or halides, because they only want to form 1 bond. They certainly couldn't be made to make chains, right? So even though each of these carbons is divalent, as we talked about as it should be last time, we want to make chains of carbon atoms, not atoms of different types of elements. So that would be no good. I guess one exception for that is we do occasionally see peroxides. That would be where we have 2 carbon atoms connected together in a chain. So if I had, for example, two oxygens, this would be a peroxide. And so peroxides are pretty reactive because oxygens don't like being chained together like this, like carbons are happy to do. So if you need to draw peroxide, you can. You just want to keep in mind, right, that they're pretty reactive. All right, so you want to draw all constitutional isomers with the molecular formula C4H10. So the easiest way to do this is probably just to do a straight chain and then make sure the number of atoms come out correct, right? So if I chain 4 carbons together, and then I give each one of those carbon 4 bonds by adding hydrogens, I use up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this would be a good structure for C4H10. All the carbons are tetravalent, all the hydrogens are monovalent. So this would be one constitutional isomer. Another potential constitutional isomer is if I start making branches, right? So rather than having the carbons all out in a straight chain, if I start putting the carbons on branches. So I'm going to move this carbon and put it over here. And so that's going to give me, right, that carbon skeleton. And then when I go to put the hydrogens on, I'm going to put on 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now, I didn't draw that one great. Let's try that again. Right, and so then I fill in those with hydrogens. I got to 10, so that's going to be 10 hydrogens. Right, and then because the atoms are connected in a different way, I've got a chain of 3 carbons with a carbon coming off. The second carbon is a branch. It's a constitutional isomer of the first compound. Now, one thing to be careful about is it matters when we do the branches, like which carbon the branch is coming off of, but it doesn't matter if we take turns. So, for example, if I did that carbon skeleton and then I put the hydrogens on, I'd still get C4H10, but this compound is identical to this one because I still have a chain of 4 carbon atoms. It's okay to bend around or rotate around bonds, and so when we're looking for the constitutional isomers, if we have branches, right, taking turns is okay. We just can't, if we were to, if we had to backtrack to continue the chain, it would be different, right? So this one, the longest continuous chain I can get is 3, and then it has a branch coming off. So this one is different from this compound, but in this case, my longest chain is still 4. So this is the same as this first compound. And so I don't think for C4H10 that there are any other ways to draw a constitutional isomer. So, right, we said this was no good. And so in this case, we only have 2 constitutional isomers. All right, here's another example, but we're going to throw an oxygen in here. So, when I'm drawing these constitutional isomers, usually I start with making my carbon skeleton and then adding the other pieces on. So I think the simplest way to do it is just have a carbon chain of 4. And if we put an oxygen on, the oxygen wants to be divalent, so we'll stick a hydrogen on there and then fill in the rest of the hydrogens on the carbons. So I've used 1 hydrogen, and then I'm going to use 2, 3, 4, 5, 6, 7, 8, 9, 10. So all the carbons are going to be tetravalent. The oxygen will be divalent. The hydrogens are all monovalent. So this looks like a good structure to me. All right, so some other constitutional isomers we could draw. I could put the oxygen on. So right now, oftentimes when we're thinking about organic structures, we often number the carbons in the chains. Right, so right now the oxygen is coming off carbon 1. I could also put the oxygen coming off carbon 2. And so I could draw this. Constitutional isomer. Now you might say, okay, well, so I got the oxygen coming off carbon 1 and then coming off carbon 2, so then I could do 3 and 4. But if I went to put the oxygen here, right, if I started numbering the carbons from this side, it would still be coming off carbon 2. Or if I put it on this carbon, right, we'll just call this carbon 1, and so I still have 1, 2, 3, 4, a 4 carbon chain. So as far as the straight branched or straight unbranched carbon skeleton, we just have these 2 constitutional isomers. Because if I put the oxygen here, or here, or here, or here, right, in this case, they'd all be coming off carbon 1. In this case, they'd both be coming off carbon 2. And so this is going to be the same as one of the 2 that I've already drawn. So now we could think about putting the branch in the carbons like we did last time. So I could do this. And in this case, I think there are 2 unique carbon atoms, right? I've got this sort of central carbon that's bonded to 3 other carbons, and so he's kind of unique. But then each one of these carbons is the same as any other one, right? They're all coming off of this central carbon. So if I put the oxygen here, or here, or here, it's going to be all the same. So the 2 different isomers I could get is if I put the carbon coming off one of these carbons on the end, or putting it off the middle carbon. So I can get 2 more constitutional isomers. No, what am I doing? I already used my 1 oxygen, so the rest of these have to be hydrogens. Right, and I still have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens. So then the other option is put the OH on one of the end carbons. All right, so that's 4. Now, one thing we'll talk about in the next chapter is functional groups. And so you don't have to worry about these names yet, but you'll need to know them for the next chapter. These are all alcohols. Alcohols are functional group when I have an OH coming off of the carbon chain. And so I have these 4 different alcohols. I can also think about the structures that I can draw that are called ethers, where I'm not going to chain oxygens together, but it's okay to insert oxygens into the carbon chain. So I don't have multiple oxygens linked together, but I can break up the carbon chain by sticking an oxygen in there. And so if I consider my first right, I could do that ether where we have 3 carbons on one side and 1 carbon on the other, or I could also do it smack dab in the middle, right, where I've got 2 carbons on each side. And if I go in and fill in the hydrogens, right, the carbon is now divalent, so he doesn't need any hydrogens. And then again, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I've got my 10 hydrogens. Right, I'm going to be a little lazy. I'm not going to put in the hydrogens. I'm just going to put the dashes on here. Right, we can imagine the hydrogens are on the end to speed up this video a little bit. So I've got, so far, 1, 2, 3, 4, 5, 6. And I think there's one more. I can do ethers with this branched guy, but I think there's only one way to do the ether, right? Whether I put the oxygen here or here or here, it's going to be in between the central carbon and then one of the 3 guys coming off. So the one other constitutional isomer would be this one. Right, and again, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens. Right, and one question I'm often asked, is there any way that I can know how many constitutional isomers I'm supposed to have? And I don't know any way to tell that. You just kind of have to go through systematically, right? Start with the straight chains, right? Then start putting in branches. And then if we have oxygens, right, do the carbon skeleton first, right? Then see what are the different ways that I can fill in the oxygens. And then oftentimes, right, I'll do, right, just chains with carbons. Then if I have oxygens, I might start looking for ethers. And then if I have, chlorines or fluorines, they can only have 1. So I can't have ethers with fluorines or chlorines or bromines or anything like that. All right, so one last example. We want to draw any 5 constitutional isomers with a molecular formula C3H8O3. Now, there are a whole lot more than 5. I just wanted to do one where I had multiple oxygen atoms because I want to emphasize one particular point. Right, so the first thing I do is, all right, let's make a straight chain of carbons. Right, and we got to put 3 oxygens on. So the easiest thing might be to put an OH on each one. Finish off by giving carbon 4 bonds. Check, make sure I've got the right number of hydrogens. 1, 2, 3, 4, 5, 6, 7, 8. So that looks good. I think there are a lot of ways that we could arrange those alcohol groups, those OHs. Right? I could also do something where I have two OHs coming off the same carbon, and then an OH off another one. Right, I could also move the OH to here. Right now I've got two OHs on carbon 1, one OH on carbon 3, so I could do two OHs on carbon 1 and one OH on carbon 2. So I could do that. I could do two coming off the middle carbon and then one on the end. But to mix things up a little bit, let's draw mixing in an ether, and I still have 1, 2, 3, 4, 5, 6, 7, 8. Another thing we could do is, all right, the OH is right next to the oxygen that's making the ether, so, and it's on the 2 carbon side, so I could put it on the 1 carbon side, and that would give me a 5th constitutional isomer. Right, now the reason I wanted to do this specific example is to talk about some that we can't do. Right, and so what we wouldn't want to do is try to have something like this, where I still got 1, 2, 3, 4, 5, 6, 7, 8 hydrogens. All the carbons are tetravalent, the hydrogens are monovalent, and the oxygens are all divalent. But what I talked about before, we can't make long chains of things that aren't carbons, So linking 3 oxygens up like this, that's no good. We talked about before, peroxides are possible, where we would have 2 oxygens together, but they're very reactive, and so if I don't have to go there to get to my 5, why go to something weird like a peroxide?